Good evening and welcome to the live session for the course on computational science and engineering. It is 6 p.m., but participants are yet to join, so we will wait for a few more minutes before we get started. Thank you.
अथॉरिटी वाला जो होता है ना उसमें सर का और तुम्हारा दोनों का रहता है।
मैंने देखिए सर से साइन वाइन सब करवा लिया था। मैंने अमाउंट गलत लिख दिया, उसके साथ से बकचोदी हो गई। तो
1 लाख 80 की बचा हुआ है क्या?
नहीं, फुल अमाउंट लिखा था मैंने, बट PMRF के साथ बकचोदी 80% ही देते हैं ना।
अच्छा हाँ,
हर बार मैं
तो बस ठीक है, यही तो देना है।
हाँ, तो मैंने लिख भी लिया, मैं साइन करके आपको दे दूंगा। मैंने सोचा
तुम्हारा साइन है क्या?
नहीं, मैं कर दूँगा।
रिसीविंग पर्सन है ना?
उसमें मुझे करना चाहिए कि आप ही का लगेगा वो?
नहीं नहीं भाई, तुम करो।
ठीक है।
उनको लौड़े को पता है कि बेंचो पर वो आई कार्ड मांगते हैं क्या? कोई नहीं दिक्कत नहीं, तुम एक अथॉरिटी लेटर भी लिख दो साथ में
हाँ
कि आई एम ऑथराइजिंग उत्कर्ष। ये अथॉरिटी लेटर ही है एक्चुअली में तो।
हाँ, जो कि सर मुझे होता है इसका।
हाँ, और तुम मेरे को करोगे तो बोलेंगे बेंचो लूप ही बना दो तुम। कोई दिक्कत नहीं है, कब तक मिल जाएगा चेक तुमको?
कल।
बस ठीक है, मैं कल जाके ले लूँगा। मेरे को बस एक बार व्हाट्सएप करके याद दिला देना।
ठीक है।
यार मैं उधर ही जा रहा हूँ, फिर ये उनका रहोगे नहीं क्या? तो मैं डिपार्टमेंट
ठीक है।
बहुत पेपर आज ही, अच्छा आज ही बात है। तुम आज ही मिल जाता है।
आज मिलता है मुझे। उसने ऐसे ही बोल दिया था कि ना मेरे पेपर अप्रूवल अकाउंट से शाम को 5 बजे रेडी हो कल हो जाएगा।
तो कल मैं आपसे लोग पोस्ट में निकाल सुबह वो पहले तो इसको पूछ के आ जाऊँ। ये बताइए व्हाट्सएप करके आप लोग आज ही करा लेते हैं ना। वहाँ से
So you have to write only in that way. They gave some comments, or you can write any code. Any code, any code. Yeah. But it should be that staggered grid. Staggered grid is will come later. Download from the model. No, I mean to say, jumping into complex problem is not going to do it. You have to go suggestion. Even if you, I understand, it's okay.
department you can call right now.
Sure. Where you want to go to library or you want to see?
Just snack right now.
Sure.
Yesterday I went to that place from Hyderabad.
Oh, outside.
Then the roommates were there.
Really?
Did you try no?
Cleaning.
No, I ordered. I think they
ordered
they
means
even
you
have
have-
some member, this Nitish guy. He used to got that guy's number, and they used to give a very good discount for IT students. They're getting less percentage.
Oh my
We
god.
call and ask them, they leave it for somewhat cheaper price.
That's good, man.
I think
So
the price difference is quite huge compared to CD. That guy gave me that contact also.
you can change it also.
Yeah.
But how will they deliver it?
But I don't deliver. They deliver normally. It is there nearby only.
Oh, actually, yeah, I know. It's in Powai only, no?
It's in front of.
Then it's right.
Right. Yeah, I know. Near to the Powai hospital.
Yeah.
Yeah, I know.
And inside IT, I think they give discount and they will deliver for free. There is no.
I saw that. Yeah.
I think Google Maps only this guy got them.
I saw a flyer of this thing pasted on the lift.
Oh yeah.
Yeah, pasted over there. During Mumbai, I think.
But we go to. You want to go to Gupta? I think it's.
No, some snacks here, samosa.
Yeah, I'll just.
Sure.
Okay. 2D exclusive lens. Okay.
These are the
Using flat space solution. So you have to do that FOU. Okay. Where you are getting stuck for implementation?
See, I created the page here. So animation scheme we have to take like
Yeah.
we have to represent. And see certain courses will take they make positive when it's negative, then the minimum of that is the mass plus amount of grades or negative grades. So positive is negative one.
Okay. One D problem.
Only problem I tried, but I have not written the parallel.
Oh, one D problem also not okay. Can you do one D?
Yeah,
So one D typically shouldn't be any problem. So triangles are not started yet, right?
no.
So
It
that
is more difficult.
yeah. That is just doing some magic in creating. That's
So I will use not 20, this is just 28 numbers, not every one.
this is working, right? Or not? This is also not working. This is steady state. It should be steady state.
No, feed generation is also there.
Okay.
This is complete I wrote one now.
There are different ways to do projects. Relative, absolute, relative. There are different things to do. But like we can do like we use L1 or L2. Instead of summing up everything, you can take global, average of global. There are different ways. Not that is important. All that stuff is useless. We just do T minus T volt. That is the relative convergence. P L2 or L1. L1 is like what is being active. Same definitions. So errors you use whatever you work in FMU because that's easier. So don't do Delphi. This is not safe. Okay. Then what is that? What are we doing instead? Boundary conditions. equal to 1 is the boundary. So then why?
Left wall.
So but then why?
That is constant.
So left wall is constant. Why this 2 and
That the like he said.
give it is random it is starts from 1 to n.
Yeah. So
Put 1 to n.
1, 2, 3, 4, 5, 6.
Cell centers.
Cell centers. So if it is 2, then this is delta x. If it is 4, this will be delta x by 2.
Okay. Oh, the one is the on the
Wall.
Okay. So this is 2 and this is n minus 2.
N minus
So if this is 1, 2, this is n minus 1. So n minus 1 of this. Because it won't be matter and this also should be see to 2 to n. You should go to 2 to n minus 1 or n minus 2, whatever you have to check. This is one thing. What is n plus 1? Meaning of n plus 1? E1 of E1 of n.
This is
N plus
plus
n
plus.
plus 1. Excluding the n. Oh, then you have a mesh size of until n plus 1, not n.
Yeah.
Oh, then this is correct for me. Then 2 to n only.
Yeah.
This is n only. Then it's not n minus 1. That is correct. So where e volts are once 1 comma n plus 1. So e greater and e 1. Why once?
Just to initiate 602.
Okay, it's not 0. So you initiate it once.
Good evening and welcome to the live sessions for the course on computational science and engineering. This course is taught by Professor Ashok Dey, who is a member of the faculty of the Department of Aerospace Engineering at IIT Kanpur. And I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. Over the past few weeks, we have discussed several mathematical preliminaries which actually uh, form the backbone
This is
of any computational scheme, and in general are
E minimum of 5.
the foundational building blocks for describing any physical phenomenon
I minus
in a mathematical
No,
form,
all 3.
that is
I
to
plus 1,
say,
I plus 1
for
is 5.
modeling of any physical
So there is no
phenomenon or
question for
process.
that also. And why you are dividing by
And
increase the
now that we
dimension,
know
that
how
also
to, say,
so if
analytically
you
solve
always
for uh, ordinary differential equations and to some extent for partial differential equations as well. Now is the time to actually delve into the implementation aspects,
case
that is,
consideration
how are
A part
these
of abstraction.
models or
So
these mathematical equations actually solved in a computer-based solver, what goes on behind uh, in the backend
so current
of
current volume are same.
common computer-aided engineering software
Volume
packages,
is different for
this point
and
is
what are the considerations when we are trying to implement the solution algorithm for, say, any a differential equation or a model based on a set of governing equations and in a computer and solving it. So in the last session, during uh, the solution of few PDEs, we were introduced to certain numerical schemes such as finite difference, center difference, forward difference, backward difference. We also spoke about explicit and implicit schemes. And one important step that we took was to write what we called pseudocodes of those solution schemes. Now, a pseudocode, if literally translated, would just mean a false code. So why are we working with pseudocodes and why not with actual codes? So a pseudocode actually is written in a language that is easy to understand for us, and it is basically a collection of logical statements that outline the flow of any solution algorithm. Whereas a code is has to be written in a certain language, and therefore it will be bound by the syntax and semantics of said language. Uh, Say how you write uh, any algorithm, such as a solution of a tridiagonal using a TDMA or tridiagonal matrix algorithm, will be written very differently in Fortran compared to C++ compared to Python. So while the actual implementation of any such algorithm will involve writing it in a coding language of your choice or based on the demand of other requirements. Say some language may be more efficient, other might be more robust, or sometimes you might need backwards compatibility, in which case you would like to write with a language which has legacy. Whereas a pseudocode, since it basically just outlines the logic, it is suitable for writing in any code, and even more importantly, since it does not really involve any syntax or semantics per se, it is very easy for us to understand. So today also we'll talk about certain topics that were covered in the lecture this week, such as bisection method, Newton's method, second method, and so on. And one important thing we'll do is also we'll also write the pseudocode for implementing any of such solution methods in a computer program. Okay, but first let us start the discussion with errors and binary machine numbers. So Professor Day has already discussed these aspects in great length in his lectures, but we'll just touch upon some of the more important bits before we move forward. So when representing machine numbers in a computer, the extent of precision is not arbitrary. That is, I cannot have or I cannot represent a number with arbitrarily high precision. While writing it down, we can have as many decimal digits as we care to represent. But is it the same when we are trying to represent a number in a computer? So a 64-bit, also known as a binary digit representation, is used for real numbers. In such a representation, the first bit is a sign indicator denoted by S, which can be 0 or 1. Typically, 0 would mean that the number is positive, whereas 1 would mean that the number is negative. This is followed by an 11-bit exponent C called the characteristic, and a 52-bit binary fraction F, which is called the mantissa. The base for the exponent, since we're dealing with binary numbers, of course, is 2. But other numbers are also popular, such as uh, we have base 8 representation, we have decimal representation, we even have hexadecimal representation. However, the most common, as we are well aware in computers, it's the language of zeros and ones. So binary number representation is the most common. Now, 52 binary digits correspond to between 16 and 17 decimal places, and thus a number represented in this form has at least 16 decimal digits of precision. The exponent of 11 binary digits gives the range of 0 to 2 power 11 minus 1, which is 0 to 2047. However, using only the positive integers for the exponent does not permit an adequate representation of numbers, and thus, rather than having numbers from 0 to 2047, we have the values of the characteristic from minus 1023 to positive 1024. And to provide a unique representation for each floating point number, sometimes a normalization is imposed, and this gives us floating numbers of the form minus 1 power s, 2 power c minus 1023 times 1 plus f, where again s is the sign, or s denotes the sign, c here is the characteristic, and because of the way it is written, c minus 1023, when you have the value of minus 1023, you can have a very large negative number. And when you have 1024, you can have just 1. F again is the mantissa, And this is how numbers are represented in a computer.
and everything is indexed properly, then it becomes a bit foolproof. And do not worry about typing
Now, let us look at some examples and try to understand
it's not
what is going on.
important to go into until you
So we have an
actually
example of a machine number given here,
HPC
which is really a long sequence of zeros and ones.
and
And the
you want
space in between is
PhD
for
making faster.
making reading
Those stuff
easier.
are not
The first number, as we discussed, denotes
not
the
expensive
sign.
to see, but only
Since it is zero here, we can presume that the number is positive.
only will have this kind of problem. For expensive,
This is also written here. So the leftmost bit is s equals zero, which indicates that the number is positive.
this
The
P will
next
be
11 bits, so 1, 2, 3, 4, 5,
and we'll
6,
have to
7,
process
8,
it
9, 10,
again.
11, yes,
P plus 1 minus P here,
give the
P
characteristic
minus P
and are
minus P here,
equivalent to this decimal number, that is 1 into 2 power 10 plus 0 into 2 power 9,
and so on.
so on, plus 1 into 2 power 1. That is, we start from the back, we raise this first digit to 2 power 0, multiply it with 2 power 0, then with 2 power 1, and so on till 2 power 11. And this gives us the number
Okay, so
1027.
that is like in final difference again. It's
So the exponential part of the number becomes 2 power 4.
this one.
Now, this
So for
final
example,
last set of digits, which is actually
those
52 bits, specify the mantissa,
then 0.
and this is how they work.
Okay, Taylor series expansion you can do. Those are easier. But just to see in objective
Yes,
way,
the number which is
just do one
being
thing.
represented here is
So
actually
d square d by dx square means d by dx minus d by
27.56640625.
dx by dx. So this is it plus half
Now,
minus half.
we have this number
This is like d by
27.56640625. Can I
so
represent
then d
a
by
number
dx
such as
plus half will be p plus 1 minus p plus
626?
1
That is,
dx
in terms of real number,
minus
just the next number.
p 0 minus
Or
1
is there any limitation
by
on
dx.
what numbers I can represent in the neighborhood of any given machine number? Well, the
Okay, so
next
why
smallest
this
machine
plus
number,
of minus
or
of?
the
Why
number
don't we
just
use plus of
uh,
minus of? We can,
smaller than
but
this,
it will center instead of
is
giving
given
center
here,
difference, we'll get some other difference.
and the next larger one is given here as
All
well.
those forward difference, backward difference,
So we
and
see that
try to
this
reverse
series
keeping
is
the
not
AX square
really
root.
continuous.
Always keep
In
in
fact,
mind
we have
that
discrete levels,
AT AX equal to
and
B.
any
If
number in
AX is
between
similar to
must be
B,
represented or
you have to check whether
approximated
AX is
by
symmetric or
either of these
forward
bounds.
different or not.
That is to say, the original number that we saw on the
Like
last
you
slide,
inverse arithmetic
this one,
imaginary number. Like you can check eigenvalues of it to see what is the time step is maximum. Maximum 1 by maximum of eigenvalues will be the given
represents
time step.
not only its
Minimum time step, given
exact
time step.
decimal equivalent,
Again,
but also
these kind
half
of
of the real numbers
tricks are there to
that
see
are
whether the
between
code is running or not. Then if
our
you
original
check
number
your
and the
imaginary
next
numbers, because we know
machine
the
number,
properties of it,
as well
we know
as
all
the
different
original
values
number and the
for
next
certain properties.
largest machine
If you
number.
give in crazy eigenvalues, then you will think that
As
okay, I wrote some code mistake.
this number
This
actually
is what
represents
I did.
any real
So there are
number
different
in
ways to
this
keep
given
track of
interval
it.
closed
Like what I will do is what I will do is
27.566 onwards to
uh,
open 26
put 0
27.566 is
put 1 in the
40625.
temperature, run for one time step. See if then what will happen is 1 will
Now,
spread
because
into
of
the 3 channels.
such constraints, or because of the discrete nature
0.8,
of machine
0.8,
number
0.1,
representation,
0.2.
we often have to deal with
If you
things which
use
are called overflow and
1.1 spread,
underflow.
maximum principle is not holding. Automatically it
The
says that
smallest normalized
below
positive
sum is
integer
wrong.
that can be represented as
Suppose 0
S0,
here and 0.8
C1,
here,
and
then
F0
your code is wrong.
and is equivalent to the number shown here,
What is the technique?
approximately
Do one pass,
0.2221
give one
into
give
10
one one
power
time step with
minus 307.
that is just
The
one
largest
step.
number that
There
can
are
be represented
these kind of things
is
like we can do it, but
approximately
these are like required instructions. See, this one.
0.17977
Okay.
into 10
Okay.
power
But before that,
309.
we just finish this. So for example,
Thus, because
this is T, this
of
is
these being the smallest and largest number respectively that can be represented in binary system in a computer,
then it
any
becomes
number
A
which may occur in a calculation for say very
T
small changes between time steps,
T volt.
if that number happens to be
So
smaller
this is
than
0 itself. This is also 0.
2 power
T
minus
plus
1022,
T
it cannot really be represented and will
plus
result in
T of T
underflow. And
plus 1
to
minus 1.
prevent the calculation
So
from
T volt will be
or
like
the
T
program
volt
from getting
will
interrupted
be
abnormally,
0.
typically they will
Let it
simply
be
be
specific.
assumed and set to zero,
So that will
even though
be
they are non-zero and over time may add up to have a significant value.
Keyword of plus one.
Similarly, if there are any numbers which are greater than
A
2
is
power
alpha
1023 times 2 minus 2 power minus 52,
alpha dt by dx.
representing such a number or accounting for such a number during a calculation will result in an overflow,
Dx square of du over
and here we cannot really set it to an arbitrarily large value,
plus
thus the computation
plus
must stop
1 minus 2 alpha
unless there is some artificial or intelligent design
into e
where this occurrence can be detected and some suitable action can be taken.
plus also. So that's it, right?
And also it is very interesting to note
1 minus 2 alpha dt. Alpha dt by yeah.
that for the
So
number
now
0, the representation is not unique.
uniformly 1.
We have a
So
positive 0 when the
yeah,
leading digit or sign is 0. C0 and FF are also 0. Then negative 0 when that leading bit is 1, while C and F continue to be 0.
so what
Please allow me a minute, I'll just start some water.
not here. B is here.
E choosing time step.
So PU should be dependent on
Now,
PU
let us talk
because
about errors
that term is missing here.
and why do errors creep up. So typically,
This is
we do not always
PU
preserve exact
plus
precision when
equal to a
between
particular
calculation steps.
I mean I
That
don't
is
know
to
what
say, a
this
number which can have a very long or a very large number of decimal digits will be approximated as a number with some finite decimal digits, and the remaining part of it
average is working
will
out.
lead to
So
some
that should be right.
error of approximation.
I'm saying
And this
in this
approximation is of two
situation
types,
log over log
chopping
becomes
and
0.
rounding.
Right.
So if you replace all
Now,
the
for the
elements
discussion
with
here, we
0,
assume that
the
machine numbers
remaining
are represented in normalized decimal floating point form
so
to
somehow
understand the
somehow that
concepts
happens.
that is at work.
Keyword will
And
be
so
under
typically, the numbers will be
log
represented at
1 minus 2 alpha dt by
say
dx.
plus minus point d1, d2 till dk digits into 10 power n, where each of these individual digits, such as di,
D old. I think
the leading digit
just
d1 will be 1 less than equal to d1 less than equal to 9,
Okay.
and all trailing digits can be ranging between 0 and 9.
Okay, I mean we'll make this work
A
then.
number of this form are called k-digit
So now
decimal
tell me
machine
what is
numbers.
AE and AW and AP.
A is A upon delta XC,
Okay.
weight between the two sets.
Any positive real number within this numerical range
A upon delta
can
XC
be normalized to the
is
form
delta lambda between
point
the set
d1
of
d2
integers.
dk dk plus 1 dk
Why
plus 2
don't
into
you
10
give me
power n.
x? What is x?
Now,
X is an
the floating
isolated
form of
variable
y,
and delta T is the
denoted
stabilized
as
variable.
fl of y, is obtained by terminating the mantissa of y
X is the
at a
size
specified
Size
k
of the
decimal
set
digits.
okay.
So it may have any
and
uh, arbitrary
But
number
it
of
is a
decimal
time
digits,
step.
but we are only considering
Okay.
or approximating it till k decimal digits. And there are two ways to
Make
perform
it
this.
work.
One method, which is called chopping,
So any heat generation
is
will
to
be which
simply
flow?
stop
If you want to
at
take.
the specified digits. That is, we only consider decimal points till d1, d2,
Convert this
dk,
percentage per flow.
and we ignore all trailing digits such as dk plus 1, dk plus 2 till whatever number of digits there are.
20 volt
And this will produce the
power
form
and will give
fl of y
both
is
sides
equal to point
one
d1,
one
d2
second
till
plus
dk into 10 power n, and
conversion.
we see that all the trailing digits such as dk plus 1, dk plus 2, this could have gone till some arbitrary
PU alpha
t k
is
plus p
20
digits.
inches
All of these are ignored,
by
or
10
so to say, they are chopped off.
zero, right? Zero or one.
What is that other method that we are all familiar with and have been using, say, at least since high school? It's called rounding.
Old.
In rounding,
Oh, oh, sorry.
whenever the say again we are considering till only k digits, but we still look at the k plus 1th decimal. If that decimal number happens to be greater than equal to 5,
Because
we add 1 to
we have to
dk
calculate when
to
we
obtain the
integrate this
floating
we have to
approximation of y,
because we are not doing
or
integration.
floating representation.
So I'll make it
And in
plus
this
one
case, we say that we have rounded
it's all
up
same.
because
So
the number we have now is
plus
slightly greater than the original number.
delta T is a plus
when
X will equal to 0
the k
comma
plus
n
1th
comma n plus 1.
decimal number
Can you print it?
is less than
What
5,
is that process?
we let it be and we simply chop off all the digits apart from the first k digits. Now this number is just slightly smaller than our original number, and so it is said that we round down. When we are rounding up, the digits and sometimes even the exponent may continue to change.
0 to 1
And
and 32.
to
So
better understand these concepts, let us have a simple example. So determine the
so it is
5-digit chopping and rounding values of
no,
pi.
I'm just wondering whether how it will.
I
So
will just
what is it?
write
You have the length of
a
size
few
is
digits of pi
Length of size
from
is
my scientific calculator.
so length of size is 1
and
So
from this center to center or
3.14159264.
no it goes and 12 cells, grid points, 12 cells we have to do.
okay. So if it is 12 cells, first
And let us see how many digits we are
row
having.
is it 0 and 1
So
and remaining will be in between. Okay, okay. Oh, this is what it is. This is
this
0
is
to 1.
1, 2, 3, 4, 5.
Okay, okay. So we have cell
So
centers
till
and
here.
the mapping digits that you told
So
me that.
the floating point representation of pi,
Okay, this is 0 to n comma n plus 1.
we will move after the decimal point. So we'll start with 0.3141.
So this one grid point in between, so we have to
When we
make
are
two
chopping it, we
periods.
simply stop after k decimal digits without any consideration for the following decimal.
So it has 13.
And this will have 10 power 1 since we move one position to the right of the decimal,
10 grids will
and
have control values will have 13 values.
this is 14 by chopping.
Epsilon is what? Some
Epsilon
power.
is a tolerance.
So
It is
we
also
can
known
match
as the
this
number we can round by rounding
3
off,
to 2 into n. So
and
n
that is
equal to del
3.141.
w del x w equal to
Originally, this number is 5, but we see that the k plus 1th on decimal is 9. Since it is greater than 5, we add 1 to
so
the
then we have left this
preceding
term.
decimal.
So if I mean each
So
step
it
is
becomes
each step that is
3.1416
k by del x is equal to
into
we
10
are
power
taking
1.
this portion.
And in this
So
case,
and
we have
usually it's better to multiply x
rounded
where
up.
del x is there to make life easier. But you can multiply here also. There is no problem. But you have to match the units.
A very important concept
So
that we
Again,
often
you have
encounter
not matched.
in
dy
any,
dx is
say,
other than
computer-based
dx
solver
you
or
matched by
iterative solver
dx square, right?
is
Other
the
than that
concept
it is
of
gone.
convergence. And
So where
often,
is that
if you're
convergence?
working in numerical modeling, you might have encountered a problem where your solution simply did not converge. So, what does convergence mean, say, in layman's terms? When we are solving analytically, we have exact solutions for our problems.
So
And
if I
so I
give
know
you
that
that A is what per meter?
there is only one unique solution
Usually
that I am
first
trying
what
to
we
arrive
do,
at.
right.
There is a set of solutions, but it is well
because
defined.
the matrix properties also matter.
And given the right choice of method, I will arrive at that solution,
No,
say in a single go.
but AP will become
However, often we are dealing with
this tell me what
uh,
you have to do it first.
equations
Then
or mathematical forms which do not really have such closed form or exact solutions. But does that mean that we give up and try not to solve it? Of course not. In such cases, what we try to do really is to have iterative solutions where
So this P into R of n
we
plus 1 equal to 2 into k into
start
n
with
into
some
1
guess
so
by
what
value
are the
in
direct
certain
correlation
cases,
given by this?
and then we try to correct this
these
guess
values I'm not going to
so
check.
that we can minimize
But it
the error
depends on the
between
right now. K
our
comma r per meter Kelvin and you are dividing it
approximated or guessed
x into
solution
r. What is r?
and the exact solution. Now, it might or not even be possible to have that exact solution to check what is the error, but
Oh, this is
if we see
this
that
is going to
based
be
on certain criteria, the change in
convergence
our
criteria
iterated
in the
solution
right
over
direction.
every iteration is becoming smaller and smaller and smaller, so that after a threshold value, it can be said that the solution is no longer appreciably
Because
changing.
you are not aware
We
of
can say that the
the
solution has converged.
notations.
We have also
What is
looked at
basic
the
notation?
concept of
So I
convergence and
don't know the
divergence when we were
basic
dealing with
notation.
series,
And the thing is, I
and
have crazy notations.
there were certain criteria to check whether some series
But
is
I
converging or
don't know
whether
the
it is
right term.
diverging.
Give us, give us. People write the reasonings as
Here
per
we
unit
also
terms.
have a formal
So
definition of
there is some
convergence,
unit tests
and let
based
us
on
go about it.
matrix properties.
So
Integration
suppose
should
The series Pn,
those kind of
where
stuff.
n goes from 0 to
But
infinity,
like,
sorry, the sequence Pn,
are we,
where
if
n
we
goes
take
from
one
0 to
function,
infinity,
is it running
is
for
a
infinite
sequence
string?
that converges to
It is
P
string symmetrically, asymmetrically.
with Pn
These things
not
need to be
necessarily equal to P
after
for
this
all. That is,
to
if
make
I
it
take,
equal
say,
to.
five numbers of this sequence, will the sum still converge to P? No, it's not necessary. What if I take 10, 20, 50? Even then, it need not converge to P. But what we are saying is, if n is sufficiently large, and by sufficiently large, it's basically as many as you can accommodate, then it should converge to P. That is, if you have infinitely many terms, it will equal P. But if you have finite terms, it will get very close to P. The more terms you keep adding on, the error between this approximation and exact value of P will keep on decreasing.
Dx is that
If positive
spherical
constants lambda
rectangle.
and
So like
alpha
this
exist
left and right square
with
is the same.
limit n
And
tends
then
to
there is a
infinity,
dx. So
the
del x is
modulus
taking
or
that.
absolute value
Del
of
x
Pn
is
plus 1
x.
minus P
Del x is on
by
x.
X
Pn
is the
minus P
distance between two
raised to the power of alpha
uniform
equals
rectangles
lambda.
dx.
Then the sequence Pn, where n goes from 0 to infinity,
Here x is taken
converges
as
to
Like I
P
told you, no,
of
like
order alpha
so you
with
define an x grid.
symptotic error constant lambda.
X grid, okay. X grid is different. That
An
is
iterative
okay. Now
technique
I understood.
of the
Okay,
form
I think I got the
Pn equals
because I have
some
not
g
qualified for
Pn
this.
minus 1, that is to say,
so A
for
cannot have
the
x.
nth
So I
step,
got very confused here.
our
So
guess
Because I am also
is
confused in my
obtained
mind.
as
I
some
wrote this right
function
only for
g
your
of the previous guess value.
this is fine. So I think x
That
is
is,
already
the
there.
value of
Now
p at the n minus 1th step is said to be of order alpha if the sequence Pn, where n goes from 0 to infinity, converges to the selection P equals g of p of order alpha. In general, a sequence with a
so
high
can you
order
go
of
to the slide?
convergence converges
So now
more
can you go to
rapidly
parts?
than a sequence with a lower order of convergence. And between the asymptotic constant and this order, while the asymptotic constant affects the speed of convergence, the impact or the effect of the order is far greater.
Bank of India. Oh, they're sending to other
And
accounts also.
typically,
Yes,
a lot of attention has been devoted to two particular cases. When alpha is equal to 1 and lambda is less than 1,
So about this
the
account you
sequence
have
is said to have or said to be linearly convergent. If alpha is equal to 2, the sequence is quadratically convergent.
outside Canada, they will give check. And we have to go there and deposit check. Then I
Okay,
said, then I
now
will
let
not
us
send it.
discuss about errors. Professor Day has already described errors at great length, so I will not
So
really
I think units are
uh,
matching, okay. We can
go into the theory.
yeah.
We'll directly look at an example, and just for reference, I will write the relevant formula here.
hold off on units are possible.
So, in typical representation,
Same on the
the
same
exact
order.
value,
So yeah, hold on.
Hold on.
say in such case, might be represented by P.
No.
It's
Its approximation
Oh, nice.
yeah, yeah. To 8. Now
will be
we should move to.
represented by, say, P star.
It will go to next time straight.
The absolute error
Why is it not going to next?
will be
Close it to go to next time
the modulus of P minus P star,
Oh, I think we have to put it inside the while
and
loop.
the relative error
For loop, right? Or while loop?
Why loop only?
While loop only.
will
So
equal modulus of P minus P star
why it is
by
not going to? I think the error is
modulus of
lower
P.
than the exited or something.
I know.
So what we
So
have to
now
do?
that we have for the formula here, let us try to work out these examples. So
Write display error
we are
message.
asked to determine the absolute and relative errors in approximating P by P star, and P is equal to, in the first
Solve
case,
it, solve it.
Yeah, yeah. 0 to 8 error not
0.3000
errors. Okay, okay. Can you go to the top?
Ah,
into 10 power 1,
And
yeah,
solve it.
option.
Yeah.
and P star
I think you can keep
is
running outside the loop.
0.3100
Outside the loop.
into
Yeah.
10 power
This
1.
display plot and hold
In
pause
this
button.
case, The absolute
Display
error
tolerance, right?
Display tolerance, and you're counting the iterations.
is modulus of p minus p star,
So plot you can do it outside. Control X.
which in this case will simply be 0.0100
Total 4 lines in the matrix are not in the
That lot
uh,
depends on
modulus of negative
the
0.0100 into 10 power 1 or zero
now run.
point 0.1. The relative error in this case
IET means more conditions.
equals
So error is 10 to 2 power minus 2.
modulus of p minus p star
How come it is 2 power
by
minus 2?
modulus of p
That means if you exited. So why error is so low?
by 0.3000 into 10 power 1.
Then t old n plus 1 also should be updated because that will be
This
the next
comes
step.
out to be
right.
Or you
P old n
basically zero
plus
point 1
P
by
length.
yeah,
p 0.333 say 3 bar into 10 power minus 1. Let us also compute these values for the other two cases, and then we'll be able to comment
it doesn't matter
on the
which
absolute and
one.
relative errors.
Right.
So
So one more thing. Okay.
for the second case,
So everywhere one is there. We initiated two points. Put 800 on one side
is
and on other
0.3000
for t old 2 to n is 600.
into 10 power minus 3,
Uniform, like prod was at
whereas P
0.2
star
and
Okay.
600 initially.
So
is
800 and 600 and
0.3100
TU will be function of old T old will be updated. The last
into
mention
10
of
power minus
the
3.
writer boundary is like this. Then y2 minus u max
Again, absolute error.
no, I think this T old equal to TU already wrote. That is not it.
Ah,
Sorry. Right. That is not it. Why this one maybe it ran a lot of iterations.
Minus 0.0100 into 10 power minus 3, 0.000.
See, tolerance should be where it is less than 840. See, you error
no,
should be less than.
So perhaps
it
we have
is
just better to like
not
0.1
very
into
clear.
1 minus 4.
Wait, once it is less than the tail, what
The
will happen?
relative error
See, the thing is tolerance is for the value,
Right.
and we just call it error L2 or something.
Ah,
So epsilon tolerance, I got confused. So one iteration itself it is going. So how come?
I think we can add now that Q generation.
That shouldn't be an issue. So T mu is T mu of 1 equal to
is
0
zero point 0.1 by
what will
3,
be T mu of n plus 1?
0.3333 bar into
No,
10
it
power
will be
minus
1.
1.
So
For the third case now, E is
or we can just
0.3000 into 10 power minus 3, sorry, into 10 power 4,
Yes, 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 yes. PU. Ah, no.
yeah,
and P star
What is that
is
yellow bar?
0.3100 into 10 power 4.
unnecessary. Okay. Saying it's unnecessary. It's okay. No, yeah, there is something missing.
The absolute error
So here what is going A equal to K by T is C. A equal to rho CP x by time step. Time step is x square Px square by 2 alpha. Px square by 2 alpha.
0.1 into 10 to the power 5,
No, just make it very critical.
the relative error
Or you can for flow problems you can make it 0.1 also. Like I said, you can make it 0.001 just to get good results. Nobody cares.
Right.
I mean, this is like pass fail category, right? But that they will not check if they will
Sorry, this will be to part 3.
So all this under this matrix operators versus that vector operators, floats, some MATLAB type definitions are not dynamic. No? That is also there. That also once keep in mind. Sometimes if you write one in a bracket, it will do matrix operation, which will be different. That also
And
we
so
need to
very
know.
interestingly,
This
what we can
definition
notice
will do
is,
MATLAB. If
in
it is
each case,
linear, it will not compile anyway. If you do type it at all.
the
But if
relative
it
is
is dynamic,
the same,
yeah, that is comfortable in some places,
whereas
maybe not so
the
good in
absolute is
another places.
can vary by several orders of magnitude.
This is the key.
And this throws some important light on the importance of choice of which error metric you are using to distinguish or compare cases, because uh, as yes of the three cases, the relative error was the same as the absolute
See,
error
that 800 did it went into 600? That's what I'm saying.
was drastically different.
There is something wrong.
Now, let's look at a few theorems of calculus, which are fundamental to the solution schemes or solution technique that we will study. The first is Rolle's theorem. Suppose f is continuous on closed AB,
Can you make
C1 continuous, and
A
f
imply X
differentiable on open AB.
comma
That is,
A
apart from
imply
the
X?
two endpoints, it is differentiable throughout AB. If f of A equals f of B, that is the value of the function, and both the endpoints of the domain is the same, then a number C
Comma
in open AB exists with f prime of C equal to 0. That is, there will exist at least one number such that the slope of the curve at that number in the domain is equal to 0. The second is the mean value theorem, which says that if f is C1 continuous on closed AB and f is differentiable on open AB, then a number C in open AB exists
yeah, yeah, yeah.
with
This you
f
already
prime of
said.
C equal to fb minus fa by b,
And then
say.
start if you try Python case, what about indentation?
That is to say,
Everywhere it is
if
optional.
we
Here it
join
is not optional.
the two endpoints of the function
Indentation.
with a straight
The
line,
tab space.
then
Yeah,
there will
that
exist at least one point in the domain, the slope at which
There
will
is, and
be
when you go for
parallel
Fortran,
to, or be
and
the
you
slope
go
will be equal
and
to this
it's better to
slope.
swipe instead of like this. Swiping like this will get give will be crazy
Next is
mean
the
value.
extreme value theorem.
And
Again, if the
finally the
function f
measure by this
is
extreme value.
C1 continuous on closed AB
See that time step is 10 to the
and
minus second.
C1 and C2 belong to closed AB
So
with
now we will
function value at C less than equal to fx less than equal to function value of C
so
for all x belonging to AB.
what is alpha now?
Addition, if f is differentiable on AB, numbers
A2 is 10
C1
power
and C2 occur
A0 is
either at the endpoints
10 power minus 9. That
or
is too small.
where m is 0.
So that means
And the theorem is basically what we use when we are trying to find the maximum or minimum of a function. We set the derivative to 0
yeah, alpha is 10 power
and
5.
check whether the derivative is greater than 0 for a minimum or less than 0 for a maximum.
Yeah. Rho is what? 10,970. They gave these values.
We already do that so this must be the
Rho CP.
intermediate value theorem.
See, alpha is k by rho CP. Do k by rho CP? Yeah. Now we are running.
If f is C1 continuous on JB and
See, now it
k
is.
is any number between f
See,
of
now
a
it
and
is
f of b,
increasing. Now it is
then
increasing 800. So
there
now
exists a
wait,
number c
you
in
can wait
an
this
AB
all the time.
for which f of c is equal to k.
Can you stop? Stop.
The actual value of this theorem comes to light in the case when k is actually equal to 0. So in case like this,
like running.
this is how our function is varying.
I think we kept it only one file left there.
And
So
we
we
have
didn't do the
number
whole
k,
file.
which lies between the value of the function number is
So now, so what do you want to do next?
and this point is
I'm having more fun than you are.
Yeah.
What is next? See, solve one problem. This is it. Now you do heat generation sources, anything you want, only in lower S2D.
now
Only
k
one.
in this
You want to do one
zero
D?
is a value which is lying between these two numbers.
2D first.
2D,
So there exists
then
numbers
F equal to y
for
is
which
equal
f of c is equal to
FYSY
k,
is just
or
you do
there will exist
exclusive
these
first.
numbers
Then while doing
for which
FYSY,
the value of
make sure
function
that your
is equal to
limits are
k,
matching and
or
plot
where the function will go
in 1D,
to 0.
doing 1D, plot U at plot fluxes. See if any spikes are there. It shouldn't
The
go
next
very
is
high.
the theorem that we have all
Something
frequently encountered
questions are there.
in calculus
Defining ways.
called
So
Taylor's theorem.
Have you tried
Suppose
coding
f is
this
Cn continuous
calculus
on closed V, so
like
that the n plus 1th
for
derivative
2D
of f
equals to,
exists on closed AV.
that is very simple
X
to
naught is a
so
number
that
which belongs to closed AV. Now, for
and
every x belonging to closed AV,
this is good in learning good
exists a number zeta x
no.
between x
Extra
naught
issues in 1D
and x,
conduction, 2D
with
conduction,
fx
same
equals
process.
n
2D
xn plus r and
instrumentation,
xn.
Neumann
What are
conduction,
Pn and Rn?
and then
Pn
you
is
go to that one.
f
You
of x
cannot
naught
write that. It's
plus
impossible to
f
write standard
prime
rate or
at x
first
naught,
effect without
x
writing
minus
only the
x
first
naught
working solutions.
plus
I
f
think
double
I tried
prime
this
at x naught by
earlier
2
in half
factorial
an hour, then
x
only
minus
you
x naught
use.
square
What is the point? You cannot
plus
modify that. One
net
moment
derivative of f
you will
at x
be
naught
explicit and
by
stupid.
n factorial
You will be able to do the
times
remaining
x
parts
plus
of
x naught
what you're saying. Say,
or
so
the
by
familiar
taking
Taylor
standard rate
series
conversion, simple will come. How do you write
sigma
simple
k equals
plots
0 to
and
n
all those things on your own? How can you modify this?
fk
To write the
at
implicit
x
also
naught
very easy.
by k
Writing
factorial
implicit
x
is
minus
just
x naught power
stretching the
k.
boundary. So
Yeah,
even
This
the
is the
five,
Taylor
I've got a
expansion.
question like how
The
to
term
calculate this.
Rn consists of the
so
remainder
even
term,
the 5 minus
that
5
is
plus will be gone.
f n plus 1
Only the
zeta
theoretical
x by
Yes,
n plus 1
Rn will be
factorial
zero. How
times
do you solve it? Now
x
you
one is x naught
some iterative.
yeah. So that's
plus 1.
there are ways to like first you try to solve this in a paper. Like for example,
Now we come to the bisection method.
input 1,
Suppose
2, 3,
f
5.
continuous function defined on the
Yeah.
interval closed AB
Let's
with
just
f of
generate
a and
make one
b
boundary
of
variable. That
opposite
is
sign.
enough just for the same. So now
The intermediate value theorem then implies
in Excel
that
sheet,
a number p exists in AB with f of p equal to 0, because k equal to 0 is a value which is lying between f of a and f of b, because they are of opposite sign. So either a is positive and f of b is negative, or f of a is negative, f
P1
of b
is
is
the
positive.
boundary, P left, P right, into equal to
And although this procedure will
P1
work when there is more than one root
minus
in the interval AB,
less than that,
we assume
right?
for simplicity that the root in this interval is unique, or that is there is only one root.
So 1 minus
In the bisection method, as the name suggests, have
plus
a repeated halving by sub-intervals of closed AB. At each step, we locate the value of P.
P4 will be P4 of 1 minus
And this is how the algorithm goes around. So to begin, we set
so
A1 equal to A,
this is the explicit
B1
statement.
equal to B,
So P1 is given in the keyword only.
and then compute the
There is
midpoint
no
of
A in
A and
question.
B,
We are not
set
finding
it
any
A1.
since it is time marginal
That is,
multiplication.
B1 is equal to A1 plus
And T2 equal to
A1 by 2, or
1 minus
A1
2 into
by 2,
alpha dt by dx square from discretization.
something
This
like
combination of
this.
present point
So
and its neighbors. So it will be the function of like that. And for doing explicit, implicit, you
say
solve
this
like
is
this.
my function.
So this is what we wrote. No, you cannot
This
say that.
is
You will understand. You,
A,
I mean, you know the derivational theory with respect to what A
and
double
this
Yeah,
is
is,
yeah,
f of A,
and it ended up looking like this.
and f of
I don't know why in that slide that he would apply is not there. It
I
won't
will
show.
take the midpoint of A and B.
He might have
It
put
lies
this
somewhere
something
here.
not updated it or something, some syntax errors. Sometimes he might have forgotten plus equal to, and he
Is
might have
f of
misconstrued. Something will
p1
happen.
equal to
You
0?
cannot have
Then
directly
the root
it's a neighbor.
is simply
That is
p1
not
because
difficult.
that is the root, the
I mean,
function goes
think
to
about
0.
it. So now what
And
implicitly
so we
we
are
are
done.
doing is,
But as you can see in this usual case, it need not be
So I should have not do that
always always. They will not be always equal.
candidate for
Now, if f of p1 is not
so
equal to
T1,
0,
T2, T3, T4, T5
then
of
p1
U,
will either be positive or
and
negative.
will
That
in
is to
right
say,
side you will have only
its
T,
sign
T1, T3, T4,
will either be
old.
the
These
same
are known matters.
as
This is the
f
big
of
difference.
a1
So
or
and A
f of
matrix
b1,
will not be identity
such
matrix.
as in this case.
It will be one.
F of p1 is here and it is positive. So the
So
sign
only
is
T
same
zero with one.
of a.
Uh,
If
becomes
f
two.
of p1 and f of
Then
a1
linear
have the same
algebraic
sign,
inverse. It will
then
match.
the root lies
Linear algebraic
p1
inverse,
and
we are
b1
just sketching up the equations.
in this
FEM,
interval.
all this stuff is not there. FEM is like you have local K
nodes
matrix.
and then make a global
Uh,
matrix
That
out
is
of it.
indeed so, as you can see.
Implementation is very simple, sir. I don't know. See, function
Whereas
matrices
if
is not
the
very
case were
difficult.
such that
Functionals they have Cauchy
f of
function.
p1 and f of a1 had opposite
Nobody has
signs,
started with coming up
then
with it.
the root lay between
Okay, okay.
a1 and p1.
Like Rayleigh rinse will
And
be
such,
difficult.
Rayleigh
we will
rinse will
raise
get
our boundaries. In the case
solved,
we'll set
but
a2
before
equals
it that
p1,
happens, we'll calculate
where
gap
b2 remains
Yeah,
equal
yeah,
as
there is
b1,
a
and
function
again we'll
matrix.
find
and that
its
we can
midpoint, say it
calculate
will
the
lie
modulus
somewhere
of
here.
b square.
You can see
That
that
that is very elegant.
uh,
Yeah.
It's written. It
f
like
of
all these
p2
properties are all the shit I'm saying. No, it shouldn't go pi prime
has
or all those
same
things.
sign as
They are
f of
explained
b1.
by
And so
default.
now I shift my
So
boundary,
we handle
right
that.
boundary from p to
So
p2.
if you
Now I know
construct
that
a
my root is
program
bounded
like
between p1 and
AFU
p2.
properties,
Again, I
without
take the
layering the
midpoint of p1 and p2,
but CFD you have to do
with
implement
which
the P1
boundary point it has the
That's some
function
problem
sign
with
in
it. Like
common,
I'm getting
and
down
then
to
shift my
I'm not
boundary
able to
accordingly.
see where it's wrong. But in the FEM I won't get down to know. If it is
Now,
wrong, I
dissection
will get
method,
the output.
yeah,
If
though
it
yeah.
is right,
conceptually
everything
very
is right.
simple,
If you give wrong boundary
has
condition, shift to
significant
wrong
drawbacks.
degrees of freedom not
Yeah,
matched,
It
and
is
you will not get
this
results.
relatively
is
slow to
Here
converge,
it
this
gives.
is right. That is the tricky point to
So,
understand.
and
now what
the
explicitly
iteration
happens is difference
may
is
become very large
I said
before
this is old
the value
if you
approximated by s
only
as
depend on
an
the
approximate
input.
of the is small,
I mean it
good enough.
actually implicitly
And a
depends on
good
old values
intermediate
also,
approximation
but
might be
it's subjective. We have
inadvertently
to find
discount.
T1, T3 of
However,
U in
this
A,
method has the
not
very
equal to
important
T1.
property
So
that
these
always
like I
converges
said,
to a
initially
solution.
is just like some
So it might be
base
very slow
property.
and
I
it
don't
might
know
take a
whether
long
all
number
the
of steps, but
implementations
what we can be rest assured is that
to
it
this
will converge,
to pull this into
Yeah,
this.
that
which is not something that can be said
procedures are reading
every other
their
method.
feedback
It is also illustrated very well
like
in this
let's say
schematic.
I will
Say
and
we
let's
had
say
our original
I can
domain
understand where
as
feedback
A
is
and B,
and ask you
equals to
to
A1, B equals to B1.
I
We
mean,
found
I'm saying
its
saying this
midpoint, which
because
sure,
was
sure, definitely
P1,
that is not
because of
shown
the
here.
short time I have to learn.
so this is the implicit
We
expectation.
checked for the value of the function at P1, found
So
that
now,
it was positive, that is,
I mean,
its sign was the
all
same as f
see
of B1.
he mapped the Gaussian matrix
So
here,
now P1
and he
became
just kept it
P2,
all pluses
as you
between
can
two.
see
So
here.
To solve this we have to use the iterator.
The
whatever.
right boundary
So
from
this 5 by 5
B1
matrix
to
will
1.
be solved on 10 vector.
Now we know that the root is contained
3 by 3, I
in
do 3 by 3 that we
P1.
can solve.
We take
That's
the
very
midpoint of the,
I think 3 by
it
3,
came out to
5
be.
by 5 is also known. If you find an internet, it will give you analytical.
And we
Like
found the value of the function at
like 3
P2.
by 3 inverse is like 1, but 2 by 2 is b minus b minus c by
But
We
I
5.
found that the value of the
that's
function
I
has
think
the same sign
can
as
copy
f
P2
of
and then solve
A1.
it and
Yeah, yeah.
then I can
Thus,
write
I
it.
now shift my
So, but
boundary
now, how do you
and
write a Gaussian
P2
matrix for this?
becomes 2.
And then when you have t instead of
Sorry,
1
P2
t equal
becomes
to t2,
P3.
you will have 5 by 5, 25. So then t1, t2, t3, t4, but this will not be
Now,
25. This will be 25
contained
by
between
25.
P2 and P1.
So
I
if
take
these things
their
will be
midpoint again,
like this,
which is P3.
then there will be diagonal matrix
Whereas the
will
function at
be
P3
inverse
has the same sign as
of like that.
at
How do you
P2.
handle that?
So now
Those
P2 will shift to P3
takes time.
and
That we will
so
talk
on.
when you
This
start
will
doing this
continue
part.
till we convert exactly to the solution
We will
which is
discuss.
at P here.
Then I will try now step by step.
I will. So if do you want to finish today explicit read
And let
or
us
no?
uh, solve
The
an
first
example
argument
related to
was
this bijection method
only staggered
so
bit.
that
Staggered
f
bit
of
was
x
2D. Now they will come
x cube plus 4x square
always there 1 plus beta and
uh,
Okay.
equal to 0
See,
has a root
I
and
think
close
I
to
will not require three
and
volts of
use the
entire thing. If it
to
is,
determine an
if it looks
approximation
like AC,
to the
I
root
should
that is
put
accurate to at
of the
least
other.
within 10 power
This is not
minus
something
4.
like you go somewhere in
As
the
to
middle and add
first
some
is to
because
show
it is
that
not
a
required
root
for
exists
accelerator.
closed.
This is
Go
not
about doing that.
software
As we
engineering
previously
concept
saw,
is not like programmer like developing
if
stuff. I don't think any of the
the
other industries use
sign
this
or the value of the
systematic
function
working.
at the points
You
we
have to
represent,
understand how it is
the
working,
function
do
has
it
gone
systematically, and it doesn't make much time. You just
through
at least show
in
me the
between.
2D
So let us try
in
and see
very
what are the
broad lines.
signs of the
Try to
functions
modify that from
at
the other
two
non-uniform
endpoints.
and all those things. Can you show me that
F
please?
of 1
See,
is 1
these
cube
two things will be
plus
corrected.
4
Everything
square
but
minus
here.
10
I
which is
also
equal
got
to
confidence on myself that rest of the code was better.
So now you do for the heat generation on the switch it on and
minus
see.
5.
See, this is
So
what.
I will check it and then
The other endpoint F at 2
Yeah, yeah.
is 2 cube plus 4 into 2 square minus 10. This is
Oh,
basically
See,
8,
you can't do
16,
that. What I'm saying.
24
You
minus
have to
2,
do
40.
without checking units.
I was in there like hawa mein kind of.
So we see that
You wrote alpha is
the
equal to
signs are
zero.
different. Or F1 into F2
So it gives
is
zero diffusion
less than 0.
with infinite tension. That's what it is solving.
Thus,
That's why it's not getting results. And you missed the key old
the
that this is
intermediate
how
value
you have to
theorem
do the next step. Now open. So okay, what are the problems? We just write it down. See 1D heat conduction. So I
guarantees.
know there are variants. So 2D heat conduction and then 1D for
2D explicit and implicit.
2D explicit and implicit.
Thus,
So when explicit
at
pattern
least
is what?
one solution
For all this, this was the first. I think I will say this
in
is
place.
this is this is 2D non-uniform implicit.
No, these are
The
also
first
non-uniform.
part is done. Now, to use method
I got
to
16
find an
points.
approximation.
Okay.
Let us
I submitted.
go about it.
No, sorry, I'm sorry. It's finished. This was assignment 2 and this was the one I got 0 in it because I wrote this half 2 and I didn't write this kind of.
Okay.
In the first iteration,
The second one.
Yeah.
one is simply equal to A, which in this case is 1,
So implicit
and
already.
B1 is simply equal to
Explicitly
0,
heat
which is
convection.
Yeah, yeah. I mean,
And
convection means
the
it has
midpoint.
flow also.
P1 is simply
Like
A1 plus B1 by
I will
2,
just show you first
which is
this
1.5.
does it flow? Flow is
And
flow
the
is
energy.
value of
flow
the
is
function
it takes energy.
at
Flow
P1
is given to flow
is
and
1.5
you are solving
cube
staggered period.
plus 4 into 1.5 square minus 10.
Uniform,
Please
FOU
give me a
plus
second.
R
Calculator.
Okay.
and then this was the first. This was early axis electric conduction
This is to
non-uniform. So conduction between
375,
First solve this.
which is greater than
First
0.
solve this correctly.
see for this no
So
Okay.
we change the second boundary, which was greater than
this
0.
was in the grid, but later on I asked ChatGPT.
Yeah.
So in the second iteration,
Then what happened?
the first boundary remains the same.
There was some
So
transfer error.
A2 is
I
still
submitted
same as
this.
A1,
Okay.
whereas
This is
B2
supposed to come like
is
that.
now equal
That
to
is right or
B1
wrong?
Is it that right?
or
Yeah, it's right.
1.5.
ChatGPT gave me.
The new midpoint P2 is
So
You can
A2
comment all
plus
this about the
B2
calculation,
by
but
2,
thing is, don't ask it to write the entire
which
thing.
is
I
1.5.
wrote this.
Yeah, yeah.
And the value of the
There is
function
nothing wrong. Everyone of your
at
friends will
P2,
be getting from seniors, copying from
I
Google Drive,
calculated
doing
it.
from ChatGPT. This is normal. This is how it is. There is nothing wrong with it as long as you understand and making it work.
Is
So this
minus
part is taking it to
1.769, which is less than 0.
Then why did they give 6 if you
The value of the
already
function
told?
at is also less than 0. So I will shift the left boundary now. Is equal to P2
some part I got
1.25.
or I think
The
some
right
part is
boundary is still the same, equals B2
error was
1.5.
because
The new midpoint
the energy
is
Okay. Out of 10.
yeah. So
is
this
Only y was
1.375,
why said we were understood everything.
and the value of the function
I
at
said that y
P3
was
is
zero. So he said that they time is extended with 5 minutes, then subtracted and I said
okay. Okay. No, this is working. I think something. Whatever is wrong, let's see. So
1.621
follow second assignment
is
program.
greater than 0.
I know it's over. Just solve it with this
In
problem.
the
they
fourth
said that
iteration,
third one
No, third one is when?
they have not announced, but for tomorrow we have to see this video lecture and we will
when
solve
it
it.
is greater than 0, same as the right boundary will now be
But
shifted.
you can do that. Yeah, I don't
A4
know.
continues to be
I was
same as
asking
A3,
because what topics they have currently.
whereas the right boundary must now be shifted to the midpoint
Good enough.
of the previous step.
Oh, nice.
New midpoint P4
The
is
pressurizer
A4
is
is
why I
P4
wanted
by
this
2,
technical.
No,
It
no,
actually is
FEM,
7.5, but I have kept it all time.
1.3125,
I'm telling you,
and the value of the function
they are
this point
different
equal to
So, I, no, I'm in lab only. Yeah, sorry. You're
negative
instead of
0.8484,
may take another
which
but if
again is less than 0. And if it touches,
oh okay then we can
continue like,
if you don't turn off having pre-treatment then we can do. I will also.
and here I have also compiled the results. So we see that
Yeah, yeah, I will watch it. Yeah.
in this 13th step,
So what
with our
what it
error,
is? Can you open the? So they are not yet all working yet. The second assignment.
My code, huh?
Yeah. So
I
I
did
will
it
write
right
here.
for residual
So
continuation
by the
and I
13th
did
iteration,
right for regeneration index.
okay.
we
Because
in
implicit
is equal
I
to
have that time. Now I have
1.365,
understood why implicit.
1.12305,
In the program I have put
and the error
mentioning that I have to do that
is
pre-treatment
less than
analysis and then I have to calculate the
0.0001220.
threshold analysis.
Flux course can you open
Our
the second
mandate
one?
was to accurate within 10 power minus 4. So
Issues
I
at all.
guess with one more iteration, we can reach
Because I
that
thought
goal.
search for what we treatment and then I realized
We
that
saw,
actually
we see how as the iterations proceed, the values of A and B and change, and how we trying to bracket the root between these 2 points.
started learning in 9th standard C. Arrays, bubble sorting and every sorting because my father asked me to learn programming things. I was very good
Next, we will
like
write
in
pseudocode
10
for the bisection method.
till 11
But before that, let us just
in the
break for a
11th
short
we
while,
started
and
doing
when we return, we'll continue.
numbers. Then also I thought like I will go to mechanical, somehow I managed to get. And then in the engineering I didn't code and like prime numbers and all those kind of things. And then now suddenly this has come up. So when I see this kind of thing, my engine works now. But highlight is on simulation kind of lights, open for understanding electric models or that particle code also. Then I'm understanding.
No, no, this is not. So why don't you give first problem a try? These two problems, write some skeleton code, will need in rule, will debug. So once these two things working condition, then you can attempt the next problem. Do not go to that without solving
I
these
can.
two.
But for tomorrow if I have to go to class then I will have to go then I can.
Yeah, I'll be awake at like that. You can call me anytime.
Sure.
I'll be sleeping usually in the morning. I don't have timings. You can. You don't have to come to department to
Yeah.
talk. So we can meet in Google Meet.
Definitely.
I think that will give me a bit more.
Based on the numbers because I'm very good.
I can write my better in an iPad or something other. It's easier for me. And we'll make a working code. Then you can change coefficients to that match that. You can do other derivative process.
That's fine.
So implicit, I can promise you that you will implement it. It's not very hard. After that, you just okay.
So let us continue where we left off. We saw how the bisection method works, and we also did a few iterations analytically. To write pseudocode implemented in a computer program. The input for such a code would involve the boundaries can be the tolerance uh, within which we want to find our solution and the maximum number of iterations that we can afford. The output of such a code will be the approximate or the root p, or should it not be a message of failure. Say that either the number of iterations have been initialized or whatever other may be possible. The first step is to start the iteration count. So we set I equals 1 and f of a, sorry, f a equals set a. The second step, when iterative counter I is less than equal to the maximum number of iterations n naught, we do the following steps 3 to 6. We set p equals 5 times a p, set f of p this was 3, 4. If f of p or fp equals 0, or the it is interval 0.5 into p minus a less than our tolerance, then we output p and the program stops. If not, we increase the iterative counter by 1. Next step, if f of a into f of greater than 0, that is, at the same sign, then a is equal to p and f a is also equal to p, else p is equal to p. This is exactly the step we did analytically. We compared the sign of the function of the 2 points, depending on whether shifted the boundary, and this will continue to iterate as we just saw. Steps 3 to 6 will continue to iterate. If we do not arrive at a solution within the maximum number of iterations, we'll move on to the 7th step, which is to output that method is failed. After the given number of iterations, and if you are trying to essentially put what this number is and stop, because we don't want our program to enter into an endless loop and continue running unnecessarily. There's a theorem which can tell us there's a number of iterations we can expect for a bisection scenario. So suppose that is C continuous on closed area, and f of a into f of b is less than 0. That is, the signs of the function at the two sides are different. Bisection then generates a sequence Pn and f from 1 to infinity, approximating a 0 p of f with the absolute value of minus p being less than equal to b minus a by 2 power n, where n is greater than equal to 1. Using this theorem, we can actually estimate the number of iterations that a bisection algorithm will take, and we have an example here to illustrate this point. We are asked to determine the number of iterations necessary to solve fx equals x cube plus x square minus 2 to 0 with accuracy 10 power minus 3 using a1 equals 1 and b1 equal to 2. So this is the problem that we take, except the accuracy which is 3. And let us just rewrite the theorem that we have. So okay, so p minus b less than equal to b minus a by 2 power n. Which implies that b minus a into 2 minus n less than this tolerance, which is 10 power minus 3. Now we just substitute the values of b and a. Simply implies that 2 power minus n less than 10 power minus 3, or if we take logarithm of both sides, log base 10, 2 power minus n less than log base 10 power minus 3, which implies that minus n log base 10 of 2 is less than minus 3 log base 10 of 10. We multiply both sides by negative 1, and so the uh, inequality sign will get reversed. So n log 10 of 2 is greater than 3 times log 10 of 10, which is simply 1, or n is greater than 3 by log base 10 of 2. And let me just quickly compute this number. So this is 9.9658, and since n is a number of steps, it has to be a whole number, so n will be equal to whether we have reached this equation or not. So I see within 10 power minus 3, and after the 9th step, we see that the value is sufficiently close to, definitely within the accuracy prescribed. So this theorem gives us a conservative upper bound on the number of steps it will take for a bisection algorithm to achieve the desired outcome. The next method is called the Newton-Raphson method, also sometimes referred to as simply the Newton's method. Suppose that f is C2 continuous JB and P naught belongs to JB, B and F is to P, such that f prime of P naught is not equal to 0, and the absolute value of P minus P is small. What is the small? So it's arbitrarily small number. The first a polynomial for fx expanded about P naught and evaluated P. This will leave f of p equals p naught. Just the first two terms. So p minus p naught by 1 factorial of prime p naught plus p minus p naught square by 2 factorial of double prime zeta p. Term the remaining terms. Zeta p lies between p and p naught. F of p is 0. This is equals fp plus p minus p naught f prime p naught plus p minus p naught square by 2 factorial f double prime 0 p. And as we assumed, since p minus p naught, the magnitude of p minus p naught is small, the term will involve p minus p naught square will be smaller to give us p equals p naught minus f at p naught by f prime at p naught, which is equivalent to p1. This sets stage for Newton's method. Starts at initial approximation p naught and generates the sequence Pn where n goes to infinity. Uh, Pn equals Pn minus 1 minus f at Pn minus 1 prime at Pn minus 1 for n greater than equal to 1. One thing we can very clearly say is now we are not just calculating or computing the values at different. We are the and method is very powerful, but it has a major weakness that the value of the derivative is approximation. Often it has been found express is far more difficult and needs arithmetic operation to calculate than simply f of x. And the method is also stated in this useful schematic. We see how the value of the function at original guess p naught and the slope of the p naught, we arrive at the next guess value p1. Value of function at p1 plus p1 the slope intersect x-axis or y equals 0 is also in the and just repeating this operation, we try to approximate the root. We'll also write a pseudocode for the Newton-Raphson method, and again, this case, and it will be some initial guess. P naught the tolerance and the maximum partitions. This method is effective based on the initial. If someone gives a very good guess, the method might converge very quickly. However, if the initial guess is poor, the method might take somewhat longer, but still, since it converges theoretically, it will be far quick and in like section. The output of such code will have the approximate solution. Or a message of failure. In the first step, we iterated counter. Step 2. While iterative counters has many maximum number of iterations, we found the following steps. Sorry. Set p equals p naught minus f at p naught by f prime at p naught if modulus p naught is less than, then what would be and stop because we have arrived at the solution. Not increase the number of iterations one and change the value of not the updated values. We will loop through 3 and 6 till we. However, if in this course the maximum number of iterations is exceeded, then we must output the failure message. And we stop because we do not want our program to run into an infinity. Just like with the bisection method, let's also do one critical solution using the Newton's method. We are asked to consider the function f of x equals cos x cos x minus x equal to 0. We are asked to approximate a bit of f using Newton's method. So we have the bounds and we should start with some guess. And since this root is appearing somewhere in the middle, we can take an initial guess p naught equals half of this domain or pi by 4. Which is equal to 0.785398. We also need to find the derivative. So f prime x is simply minus sin x minus 1. So in the first iteration, p1 is equal to p naught minus f at p naught by f prime at p naught, which is equal to pi by 4 minus cosine pi by 4 minus pi by 4 minus sin pi by 4 minus 1. This comes out to be 0.739536. Okay. In the second iteration, the value of p2 is considered as p1 minus f at p1 by f prime at p1. So p2 will become 0.39536 minus cos 0.739536 minus 0.739536 minus sin 39536 minus. Okay. Actually 0.739085. The third iteration, P3 will be equal to P2 minus f at P2 by f prime at P2. And I am not adding the steps. Let me just calculate this. This should be 0.739. Wait. I should write more digits for the previous step as well, so that we can compare. And it was 1781. Now we see that the values are becoming really close. And for technique, P4 equals P3 minus F at P3 by F prime at P3 is equal to 17390851332 minus 0.7390851332 by F prime at 0.739085133, which is 0.790851332 minus and 5601243 into 10 power minus 11, which is really small. So I can say that this is approximately equal to 0.7390851332. Our solution is consist. The next method is called the second method, and here to circumvent the problem of the derivative evaluation in Newton's method, which can often be costly, we introduce slight variation and with certain assumptions such as Pn minus 2 being close to Pn minus, we replace the derivative term in Newton's formula to obtain the second formula, that is Pn is equal to Pn minus 1 minus F at Pn minus 1 times Pn minus 1 minus Pn minus 2 by F at Pn minus 1 minus F at Pn minus 2. And we can also see the figure on the next slide. And with initial approximation in this case, whereas in the intuition will be just 1, and in bisection 1. The approximation P2 is the x-intercept or the line journey P0 F0 P1 FP2, as you can see. The approximation and so on. Only one function evaluation is needed step for the second method after P2 has been determined. Whereas in contrast, each of Newton's method requires an evaluation of both the function and its derivative. Again, the convergence of the second method is much faster than the function iteration, but slightly slower than Newton's method. Newton's method or the second method is often used to refine an answer obtained by another technique, such as the bisection method, and this is how it is actually implemented in any commercial code. Whereas you actually start solving using the bisection because you know that it is guaranteed to converge, and just to refine the answer or to speed up the process, we after a few iterations of bisection, we may use something like a second or Newton's method. Thus, the bisection method is often used to find some good first approximations for Newton's method or second method because of their rapid convergence. We will also write a pseudocode for the second method. In this case, the input will have approximation the tolerance and the maximum number of iterations. The output of the code will be the approximate solution P or a message of failure. In the first step, we set priority counter to 2 and Q naught equals F at P naught, Q1 equals F at P1. In the second step, while the iterative counter is less than equal to the maximum number of steps, we loop through steps 3 to 6. Step 3, we set P equals 1 times P1 minus P naught by Q1 minus Q naught. In the fourth step, if the absolute value of P minus P1 is less than the tolerance, we have arrived at our solution. We simply output this root P and stop. Step 5, we set I equals I plus 1, set P naught equals Q1, Q naught equals Q1, P1 equals P, and Q equals P. As per our code, the steps 3 to 6 will be iterated till we get the solution. However, if we exhaust maximum number of iterations available and still do not have a solution, we must display the message of failure. So in the seventh step, we put that the method failed after a maximum allowable number of iterations. We stop. We have restricted our discussion to some single domain, but practically this is not always be the case. As we just depending on the type of function we are dealing with, we can of course have multiple routes within the given domain boundaries. Further, in the preceding discussion, the restriction was made that f prime of p is not equal to 0, where p is the solution to f of x equal to 0. And in particular, Newton's method and the second method will generally give problems if f prime of p equal to 0 when f of p equal to 0. This is something to keep note of because these methods might fail or might need some modifications whenever f prime of p is 0 when f of p is 0. A solution p of equal to 0 is a zero of multiplicity m. If for x not equal to, we can write f of x is equal to x minus p qx. So limit qx extends to p, qx is not equal to 0. In essence, qx represents the portion of fx that does not contain the 0 of f. And this can help us identify the simple zeros of a function, those which have multiplicity 1. An interval among p exists where Newton's method converges quadratically to P for any initial approximation P naught equal to P, provided that P is a simple zero. And to modify the Newton method to multiple zeros, this is what we do. So we start by defining mu of x equals fx by f prime of x. If P is a zero of f of multiplicity n with fx equals x minus p power m times qx, then mu x equals x minus p power m times qx by m into x minus p power m minus qx plus x minus p power m q prime. This can further be simplified to x minus p times qx by m times qx plus x minus p times q prime of x. And this term mu x always has a 0 at p because x minus p term multiplies. Q at p is not equal to 0 as per our definition. So qp by q times p plus p minus p times q prime by p is equal to 1 by n, which is not equal to 0. And p is a simple 0 of mu x. This method can then be applied to mu of x to give gx is equal to x minus mu x by mu prime x, which is equal to x minus fx by f prime x, the whole divided by f prime x square minus f of x times f double prime of x whole divided by f prime of x square, which after further simplification results in g of x equals x minus fx into f prime x by f prime x square minus fx to f prime of x, which is the more generalized form of the Newton's method or the modified Newton's method, which can also handle multiple roots. And with this, we come to the end of this session. I hope that the shared pseudocodes and the discussion that we had will help you in implementing these very fundamental algorithms in your own computer program, and also that these live sessions are helping you both in reinforcing your concepts and learning the topics taught by Professor Day, as well as in solving the assignments. And also my hope that in case you have enrolled or registered for the course examination, these classes will be helpful to score a good grade. With that, we come to the end of today's session. I thank you all for tuning in. I am Sourav Goswami from IIT Bombay, and I look forward to seeing you again next week. Thank you very much.